Yeah, I did it.
Okay. All right. Well, I'm very happy to have Zolt here to kick off our. Am I pronouncing that right? is that right?
Jolt, yes.
Jolt. Okay, thank you. I'm very happy to have Jolt here to kick off our external speaker series for the computer vision group. Jolt leads the robotics perception and learning lab at Georgia Tech and focuses on learning for sensors and robotics. And in particular, lately has worked on less supervised, unsupervised, semi-supervised self-training and continual learning, out of distribution detection, and distributed perception. So I'm really looking forward to seeing what he has to present. Thank you.
Awesome. Yeah, thank you very much for the opportunity. I'm excited to present this. We have some collaborators at UIUC and we're on the robotics side as well. So I'm excited to be able to talk here. And today I'll be presenting kind of one line of work that we have, which is Exemplar-Free Continual Learning. Just a little bit about me for those that don't know. I'm an assistant professor at Georgia Tech, and as was mentioned, we really do a lot of work in a set of areas that span actually machine learning and computer vision to applications in robotics and embodied AI. And so kind of the first bucket of work that we have done is lots of work in few shot, semi-supervised, self-supervised, and continual learning. And really what we want to do is drive the amount of labeled data down, be able to adapt and continuously learn as new out of distribution data comes in and so on. And I think there's a lot of cool ties between those areas in machine learning and computer vision to embodied AI. And we are doing sort of half of my lab now is doing a lot of embodiment based work, and that ties heavily into the first one as well. And so we're looking at joint decision making and perception. And so how do we do sort of goal-driven perception, grounding, for example, if you're given natural language instructions, grounding it in your perception, and again, combining that with things like utilization of unlabeled data and so on. And so I think there's a rich kind of interaction between the two that really has great potential for really interesting research. And we also kind of do a little bit even more roboticsy, where we have lots of multimodal data and multi-view data, for example, from teams of drones and things like that. So all work done is by the PhD students, of course, so I wanted to acknowledge them. So you'll see lots of work and slides and materials from them, of course. And in particular, the work that I'll talk about is related to continual learning and is done largely by James Smith, as well as collaborators both in my lab, other PhD students, Junjiao Tian, who does a lot of out of distribution detection, and then also Samsung research as well, including from my former student. Just to give you an outline of the talk, so I'll start with just background and motivation. I assume a lot of you already know it, and we'll really dive into exemplar-free continual learning. That is, how do we do continual learning without storing past data? And then we'll talk a little bit about semi-supervised continual learning as well, and its ties to things like outer distribution detection in machine learning, and talk a lot about future research and directions, which I think are very exciting, that really intersects all of these things that I've talked about. So just to pose the problem here, obviously a lot of machine learning is done in a way where we train offline and then we deploy models. And so this is obviously problematic for many different reasons. You know, Facebook or Meta and other companies constantly just manually retraining these models as they get new data. And this, first of all, uses a lot of computation and creates a lot of carbon emissions, but also essentially, you know, requires sort of hand tuning of these models to retrain rather than essentially retraining things on the fly. And so what you have is, in the real world, we'll have new things that come about. The example I sometimes use is in Atlanta, we've got scooters at some point that appeared out of nowhere. And so, you know, you're trying to learn about new things that come, and typically you're trying to learn in a sequence as new objects or categories or types of data come into it. And so what we ideally want to do is essentially just combine the training with the appearance of new things. And what we want to do is train models adaptively. So as you get new classes or distributions of data, we want to essentially train them on the fly adaptively, such that we can learn about the new things without forgetting old things. And this is really the problem of lifelong learning or continual learning. There's lots of different names for it. And specifically, we're interested in what's called class incremental continual learning, which is much harder, where you're getting new categories of data rather than just different types of distributions within the same kind of class or label space. And so that's essentially the key problem, is that offline training on all your data is costly, and defies some of the IID assumptions that we make in machine learning. And whereas in continual learning, when we want to incrementally learn on new tasks in a sequential manner, then we have this problem called catastrophic forgetting. That is, you're wiping away the weights or parameters of the old that were important for solving the old tasks as you're optimizing for the new task alone. And so the question, of course, is how to acquire new information without forgetting the old one. There are several lines of work, including regularization methods that essentially try to add some regularization effects where you prevent wiping away of old parameters that are effective for old tasks. There are growing neural networks where you add parameters as you get new tasks, but of course, these all have limitations, including unbounded scale of memory additions and things like that. One of the kind of common methods that has been used is something called replay, which is a very simple idea. Obviously, to infinity, it converges to the offline setting, which is just store past data. And so what you want to do is, given the sequence of tasks that you are getting, where each task consists of some subset of categories you're learning about, just store those pieces of data. And when you're learning about something new, just replay those pieces of data during training. And so this is a very effective method. Of course, as your memory goes to infinity, this is just the offline case, but obviously has a lot of different limitations. One of the ones that we're interested in is, first of all, it requires a substantial memory budget. So again, depending on the number of tasks, it's not really bounded as you increase the number of tasks. But sort of more importantly, for certain applications such as healthcare and other places, we have privacy concerns. For example, you don't want to necessarily store past data. For example, it might be sensitive. There's something called federated learning, which a lot of companies in the industry is moving towards, where you have lots of data silos everywhere and you want to train on that data, but you don't necessarily want to expose your data to everyone. And so you don't want to have to store past data to train new data. And so what we are looking at is specifically what we call data-free or exemplar-free class incremental learning. Again, the key is to learn classification models from incremental streams of tasks or sequences of tasks, but we don't want to store either complex generators like generative adversarial networks, which may overfit and also store private data implicitly, or train from past tasks that we stored. And so again, the key intuition here is to reduce memory budget and eliminate things like data storage, both for computational or memory efficiency, as well as privacy concerns. And so this is the work that I'll be presenting is from ICCV, where we deal with this problem and come up with interesting solutions that essentially just generate synthetic data using the discriminative model itself. There's lots of related work that tackle other types of settings. I'm not going to go through them, but they're all great, and you should check them out. There's lots of methods that look at streaming data and things like that, where you have one example at a time and so on, but they're all very different from our setting, which is really differentiated from this assumption that, first of all, we're not assuming you have some pre-training data or some streaming constraints. That is, we don't have to store just one example per mini batch or something. And we, again, don't want to store generators. And we actually compare to some generative models as well, just to make sure that ours is consistent with those baselines. And so the key idea here is something that actually I think UIUC and others have been part of, which is how do you essentially replay data from the discriminative model itself. So this is something called people term dreaming, where again, you have a learned model that you learned on some training data for classification. And what you want to do is start with just random data, and you sample from some target label distribution, and you say, let's say I want to optimize some dog class, the dog class, and then I backpropagate all the way to the image to generate new examples that maximize this dog score or probability. And typically this doesn't work by itself to generate realistic data. So people insert other types of regularizations like smoothing losses and so on, as well as matching, for example, image means and variances at batch norm or other types of layers that store some statistical information. So this is one approach that you can think of to actually do class incremental continual learning. The problem is that if you read the paper and the paper itself doesn't focus on continual learning, but does have some continual learning experiments. And what they show is that when you do this class incremental learning within the same data set, that is, you keep getting new categories, it actually doesn't work. So generating synthetic data from past tasks using this discriminative classifier and adding it while learning new tasks fails at doing well at class incremental learning. And so that's really the problem that we sought to tackle. So the problem is, how can we make this work such that we can actually dream or generate synthetic data, but actually have it useful for class incremental learning? And so, well, that's kind of our goal, to improve this. And in order to do this, we try to do some principled analysis to see what's going wrong. And one of the key things that we've done, for example, is look at t-SNE plots of the feature distributions. And these are just sort of nonlinear mappings to two dimensions of the feature space. And what we have been able to see is when we plot the real task one feature distributions and the synthetic task one feature distributions, as well as real task two distributions, when we just use this deep dream kind of approach to feed in synthetic data, what the classifier does is cheat, essentially. And it learns a discriminative feature space where it's putting all of the blue synthetic data into one portion of the feature space. And so this is actually not ideal, obviously. What we're finding is that the classifier, when you're training with both synthetic and real data, it's focusing not on the difference between the prior tasks, which are synthetic, and the new tasks, which are new. It's actually focusing on this difference between synthetic distributions and real distributions, because the synthetic data is not of the real distribution. Obviously, it's close to it, but it doesn't fully mirror it. And so it's essentially prioritizing the domain that is real versus fake, instead of prioritizing the semantics, which is task one versus task two. So there's some bias here, which results in essentially, when you do the testing set and you say, well, how much did it forget on the past tasks? And you feed it real past task data, it actually predicts new task labels for all the past task real data. And so this is a problem, and this is what's causing essentially the failure for this deep inversion approach. And so what we want to do is fix this, of course, and we can start from some fundamentals of what we actually want the models to learn. And this is not new, this is from prior works as well. What we want, of course, is when you're given new categories of data, we want to learn the features for that new data. Obviously, features, you can't just freeze the feature space from past tasks, because those features may not be relevant. You want to minimize the feature drift over the previous task. That is, you don't want the features to stray all the way away from the previous classifiers, because then the past classifiers won't work. And you want to separate the class between class overlap between the new and the previous tasks themselves. That's at the classifier level. And so we developed some methods that are novel to essentially target this. And what it does is it really focuses on different parts of the model using different loss functions, and freezes and unfreezes different things in order to make sure that we achieve these three goals without letting the neural network cheat, such that it just separates synthetic versus real data. And the key to approaches, we do three things. We optimize the new classifier locally. So when you were given a new set of categories, we optimize those logits independently of the prior task logits. So obviously, in the last classifier layer, we have the logits for all the classes, but we only actually optimize locally for the new tasks. And the reason we do that is because if we optimize across all the logits, the neural network will just cheat and just separate the synthetic and real distributions, because we don't have past task data that's real. The other thing we do is
question.
Yes.
Sorry, it's just a question of detail.
Absolutely.
When you optimize across those new logits, are you optimizing only the final discriminative layer, or are you optimizing the whole feature stack?
No, exactly. So we are optimizing the whole feature stack. And that forces the features to both optimize for the new classes and as well as the classifier. And I mean, we'll have other losses that prevent the feature stack from drifting from the past tasks as well. Yeah.
So you're saying that
So
just
this part
the
is
classification layer
higher.
for the old tasks is frozen, but the rest of it is
It's not
tuned?
frozen. It's just we don't do like the softmax across them. We just do
I
take the
see.
new logits only. Yeah. And the key there is if you're taking all the logits, the neural network will just cheat because there's a distribution shift. All the past task data is synthetic because that's all we have access to. All the new task data is real. So it'll just cheat to discriminate those things. So for example, it can push down the probability of all the synthetic data and modify the features to do that by pushing out the synthetic data in feature space, as an example. So that's the first thing we do. And I'll go into the loss functions as well in the next few slides. The second thing we do is in importance weighted feature distillation. And this is to prevent essentially feature drift of the old task. So feature distillation essentially says that on the data, what we want is that the predictions from the old model to be similar to the new model. And then we then only fine tune. So these first two losses, if you notice, they don't ever consider the full set of classes. And so we still have this last goal, which is to separate the classes themselves between the previous tasks and new tasks. And so what we do is we actually, in this case, we do freeze the features and we fine tune only the classifier layer across all the tasks. And so that's essentially kind of the overall framework. And so these are the three things that we essentially do. So again, it's just a clever way to basically prevent the problems that we talked about, that is separation of the synthetic data all the way by pushing it out into feature space. And so this is the overall kind of structure of the model. We have, just like all distillation methods, a frozen copy of the prior model from the past tasks, n-1 to n-1. So this is the model that was learned in the last task. And then we essentially have the new task model that, of course, is initially copied over from the previous n-1 model. But this n-1 model is then frozen. And so what we have is several types of losses. So again, we optimize locally. So this local cross entropy loss only looks at the new logits, and it does backpropagate into both the classifier and the features. And then we have the second, which is an important weighted feature distillation. So again, it's doing a feature distillation, not at the logit level, but at the penultimate layer. So the layer right before the one that gives you scores. And so it does a feature distillation loss between the predictions of the old model and the predictions of the new model, which is, of course, a common approach. One thing that we're doing a little bit different is that we're doing it in feature space. A lot of methods do it in prediction space. And then finally, we fine tune the classifier layer here using all the logits, but we freeze the features here, so we don't actually optimize this. In terms of actual equations, of course, they're in the paper as well in ICCV, but just to give you a brief kind of formal introduction, what we have is M tasks and N semantic classes. We have this notation such that the parameters at time I, that is at task I, is theta I, and we do comma n, which means that it's essentially this is the n n logits of the new task. And so if we do theta n 1 to n, that means that it's at the parameters right now at the current task, and it's all the logits from 1 to n. However, if we do theta n and 1 to n-1, these are only the old logits, the logits related to the previous tasks. And so this optimizing locally equation looks at like this, which is we do a cross entropy between the essentially only, again, the task n logits. So here it's not 1 to n, it's just the n logits, the logits for the new class. So that's all we do, it cross entropy across. And again, we backpropagate through the entire feature space. It's not frozen. To prevent forgetting, yes.
Sorry, another question of detail, if I may.
Absolutely.
This is more about the model of new but unseen classes. So in some sense, my system is sitting there, it's learning, and then a new class turns up, which it hasn't seen before, and it's got to get good at it and stuff. So generally, there are kind of two kinds of model of new things. One is sort of a direct-like model where eventually you're going to fairly quickly run out of new things. It's just a question of waiting for long enough. And the other one is a sort of a Pittman-Yor style model where you might at any point, you've got a reasonable probability of running into something completely unlike anything you've seen before. But which model you adopt seems to affect what you would do to the features.
And I guess the in terms of the actual, it's, you know, the way we evaluate continual learning, it's typically, you know, subsets of classes, right? From the same data set. And so I would guess it's the first model, I believe, where
Which would
I mean,
suggest that your features should
it's
settle
new
down.
categories.
Yeah,
Sorry?
yeah. But that suggests that your features, you want a mechanism such that your features settle down after some time and are minimally interfered with, because
Right.
you'll have seen most of the classes and you're not in for a shock.
Mm-hmm.
Whereas the second model suggests that you may need to be able to interfere with your features really substantially at any time.
Mm-hmm.
And I'm just sort of probing which side of
Right.
that fence.
I'm not sure about that, because I think in the setting, I mean, the experiment ends when you run out of classes. So I don't think that you keep on seeing former classes. You see each class all at once, and then you see a new class all at once, and then you see a new class all at once.
I think
in a
one
way,
problem is that, you know, sorry, go ahead. Sorry to
no,
interrupt.
it's okay. I was going to say it behaves, well, it's in a way, it's a more extreme version of the long-tailed case that you were saying, where not only do you not, as far as the lifetime of the experiment, you don't run out of new things to see, but you only see new things.
Yeah, I think one you know, potential downside of just the whole evaluation methodology is that typically we don't, you know, do tens of thousands of classes and things like that, where I think the feature settling that you are talking about occurs, right, when you have lots more classes. Here we're taking, for example, chunks of classes, right? So Cypher 100, and we're taking, you know, 10 sequence of 10 subsets of classes. And so
it doesn't seem to matter what the right framework here is, whether you're going to be persistently hammered with very new classes or whether, you know, it's just going to be an occasional nuisance.
I mean, I think in the end, you know, this method is geared to when you do have to change the features, obviously, because that is what our point is, right? To be able to maintain the feature space of the old one, but not like throw it into some, you know, synthetic bin because we're replaying synthetic data. But yeah.
Thank you.
Okay.
Thank you.
Yeah, thanks for the question. And so the second kind of method or part of the approach is to do a weighted feature distillation. And so, of course, feature distillation is common, but here we're doing penultimate layer feature distillation between the parameters for n and the predictions, or I guess penultimate feature predict outputs from the current model versus the past task model. And our weighting is very simple. It's just based on the magnitude of the features themselves. And this, again, this distillation is the key, is that we're trying to avoid feature drift from past tasks compared to the new tasks. And then finally, like I mentioned, we also, okay, now we need to also discriminate between past classes and current classes without causing the synthetic versus not synthetic cheat. And so the way we do that is we freeze the features and we only optimize the classifier parameters. So that's the overall kind of approach that we have. Again, it's a clever way to essentially make sure that we don't have this issue from the synthetic data. And what we show in our various results, of course, we have lots more results in the paper, but I'll show a few key ones. One is the cool one, which is, again, no core set. That is, you have zero replay. We're not replaying any past data. And this is a very difficult, challenging condition for class incremental learning and methods in general. And what you see is that our method does a lot better. So this is the CIFAR 100 10 task case with ResNet 32. And again, no core set at all. And we do a lot better as you're accumulating classes compared to all sorts of state-of-the-art results like learning without forgetting and so on. And so that's kind of the key takeaway. By the way, I didn't mention, but the metric here is on the y-axis is this omega, which is some forgetting factor. So essentially here, higher is better. And so you want less forgetting. And it's relative to some upper bound that is like the offline case where you're training on all the classes jointly. And so there's some percentage there relative to 100%, which is what the offline case achieves. And so ours achieves pretty actually good, around 70 some percent omega, which means that it's not forgetting forgetting less significantly than prior methods. And that's without no core set, and again, compared to some state of the art. What's cool is that we can actually also use a replay. Of course, we didn't actually target the scenario, but our method is actually competitive somewhere in the middle. It's not state of the art. There's a lot of like binary classifier kind of methods. So BIC is like the large scale continual learning method. And I'm sure we could probably make some changes for that, but this isn't really the setting that we targeted. But we do fairly competitively, which is nice to see, especially since we didn't actually target this setting. And of course, we've done ablations to show that these different components, essentially doing, freezing and fine tuning different parts of the model actually matters. And so the combination is actually what gives us the really good omega rather than any, one individual component of our method. Something that we've done is analysis to actually verify this feature drift analysis. So you can try to think of, I visualized the t-SNE plot where the synthetic data was out of distribution. You could see it's being separated in feature space. You could use something like maximum mean discrepancy, which is kind of a statistical measure between the feature distributions. It's like the expectation over the feature distributions or difference in expectations. And what you see is that the prior methods, again, this deep inversion method without our modifications actually, again, what fits what we saw in that plot, which is it separates the synthetic versus real, whereas ours puts kind of everything within the similar distribution, but in a way that actually still maintains the discriminability between the different tasks, which is what we want to achieve. Of course, we're doing a lot of things. So this is all training time. So during training time, we're doing a lot of things, adding some losses like distillation and so on. And so there's a question of kind of computational efficiency, and we're actually not as slow as some of the method, that BIC method that I showed that does really well with replay, but we're somewhere in the middle. Of course, this is all during training, not inference. Inference time isn't affected. And I should say, I like to give credit to concurrent works. I know how much it hurts to submit papers that others did not, or got in later. So there's lots of kind of concurrent work that have been looking at this setting of basically not using replay data, so exemplar-free continual learning. Okay, so that's one way to remove the
question about the timing.
Absolutely.
What is the mission that you've already
And I should say
we
did, so you can actually approximate the generative process using a model as well, that you don't store like a normal generative adversarial network. Like within the task, you can actually train a CNN to do the generation process as well, to speed it up. So yeah, this includes that.
Okay, cool. I just remember that deep inversion. It seemed like it was a ridiculous amount of computation.
Yeah. So that's what, this includes
data.
this includes our model that approximates the inversion process using a model locally.
Oh. Yeah. Nice.
But again, the key thing is we're not learning a global generative model of data, because I think, for example, there's a lot of privacy, possibilities there of, obviously GANs are there's lots of hypotheses that they're overfitting and memorizing data and things like that. So, and you can probably much more easily invert. Here, we're only using the discriminative model itself, and that's it. Yeah.
One more question. Why is BIC so slow?
I think from what I remember, it learns a bunch of binary classifiers. And so I think it's kind of like an ensembling-ish approach from what I remember. So I believe that's the case, but I will have to look at that. It's been a while since I looked at that, to be honest. Yeah.
Okay. Thanks.
Okay. So the other kind of cool work, and I'll go through this a little bit fast because I'm kind of running low on time, I think is rather than just generating data from the discriminative model, one aspect that I like to look at is from an embodied aspect. Let's say you're an agent, you're moving around an environment, you're actually seeing a lot of unlabeled data. And so there's a question of, rather than having a generative process to generate data from the discriminative model, can we just use the unlabeled data that's in some sense in many applications available for free and leverage that in order to prevent or reduce the amount of catastrophic forgetting that you can have. And so this is actually kind of something that other works, prior works have looked at from a web perspective. That is, you just have web data always available that's unlabeled, and we want to use that unlabeled data as sort of an anchor or somehow to anchor the feature space such that it doesn't drift through distillation methods. But what we wanted to tackle is two questions, not just how do we leverage unlabeled data in order to reduce catastrophic forgetting, but also how do you actually deal with certain things that may occur if you're actually as an agent gathering data. So one example is class correlations. So you might actually have, for example, correlations between the unlabeled data and the labeled data. For example, if you're an agent moving around an environment and you're in a kitchen, obviously the set of objects that are in there are going to be correlated. And so there's an interesting question of how can you deal with a generic distribution of unlabeled data rather than just assuming it's kind of much more closer to IID sampling from the world, which is what the web gives you. So we really wanted to tackle these two questions. And so kind of the problem setting that we call it is semi-supervised continual learning for obvious reasons. We're including both labeled data. So we're actually subsetting the amount of labeled data. So obviously results will be lower because we have a smaller amount of labeled data. And in some cases, the labeled data will follow this class structure that you might have, for example, in Sci400, which I'll show some examples of. But then you also have unlabeled data available for yourself. And we actually separate the distributions here in some sense, which we have a no correlation setting where the unlabeled data and the labeled data are not correlated by a superclass relationship. And I'll show a specific example of what that means. And then the correlations where there are some correlations between the labeled and unlabeled. And you might think this is a strange thing to say, why would that affect the algorithms? But it turns out that the algorithms developed for web data, web unlabeled data in semi-supervised continual learning actually really perform badly under this setting. And so the way we do this is in a more thorough manner or rigorous manner is actually take the superclass structure in Sci400. So in Sci400, there's several superclasses ranging from kind of animals or mammals and flowers and things like that. And so we can think about setting up our data sets such that the labeled and unlabeled come from different or same superclasses. And so in the no correlation setting, for example, we might have, orchids and so particular types of flowers for the first task, but then the unlabeled data comes from everything. So here there's no real class correlations between the unlabeled data and the labeled data. And again, this is motivated because, we want to, under the more vanilla setting, we want to see how things perform. However, you can have actually, it turns out, much harder case where you have correlations. And so here, the unlabeled data actually has correlations that is, it's the same superclass. So the unlabeled data is also flowers. It's different flowers, or it could be same or different flowers or a combination thereof, but it's all flowers. So you have again, a correlation between the labeled data and the unlabeled data. And so the intuition is that the question that we want to answer is how can we leverage unlabeled data? And of course, there's a lot of semi-supervised learning methods like fixed match and so on that use what's called pseudo-labeling. That is, you make predictions on the unlabeled data and use that in various ways. And so we're going to use similarly the unlabeled data in various ways. We're actually going to use it to supplement or replace a memory budget. That is, we're going to try the no core set kind of setting. No replay data again. And we're going to specifically leverage also outer distribution detection, which again will sort of tell us, for example, if we run the unlabeled data through the old model of the past tasks, we can tell whether some pieces of data might be kind of similar to the past tasks or not through outer distribution detection. And so we'll use it in various ways. We'll use it, for example, for class balanced fine tuning. That is, your pseudo labels actually combined with your label data that you get for your new task. You can try to estimate some things about class balance, which again, when you feed in unlabeled data, you might have different imbalanced characteristics. We'll use things like standard knowledge distillation, which can be used on all the unlabeled data. And then we'll also use standard things like fixed match type approaches where you have like weak augmentation and strong augmentation, and you enforce a consistency loss to make sure that they're similar. And so this is kind of the overall kind of approach. Again, the key thing is that we take the unlabeled data and we feed it through a type of outer distribution detection. Actually, this is from some state-of-the-art methods that we developed that was published in CVPR 2020 called generalized Odin, which is a popular outer distribution detection method we developed. And what we do is we take, again, the unlabeled data, we perform weak augmentation, we feed it through the old task model and the past task model, and then we determine whether it's in or outer distribution. And based on that, we make different decisions on kind of what losses to feed it to. So for example, if it's in distribution, that is, it's part of the past task data, then we can actually just do kind of a class balanced cross entropy loss, both for the new task and the old task. If we, on all unlabeled data, actually, we can also do just a local distillation loss. So again, similar ideas what I showed before, where you're making sure that either in feature space or prediction space, these models, the past model is similar to the new model. And then we also can do, again, the fixed match kind of method where you have weak augmentation and strong augmentation, and you apply a consistency regularization. And this can be on both the unlabeled data, but it turns out you can apply fixed match to labeled data as well. And it doesn't really matter. It actually improves performance. So those are the three kind of ways we use. And really the key thing is that when it's in distribution, we only use it, only use in distribution things for this cross entropy loss. The other parts are used on all unlabeled data. So it's cool to show that you can actually use unlabeled data in multiple different ways. When it's confident predictions on past tasks, you can actually use it in a hard way, in a cross entropy kind of loss. And in a soft way, you can use everything else in soft manners, such as distillation losses or consistency regularization losses. And so what's really cool is that, again, if you have no core sets, so we're not doing any replay, which is very challenging, and this is under the no correlation setting, we get actually significant improvements. And so actually ours is this dotted line where, again, we show it competing with other methods that do use core sets. And so we actually need about 750 examples to store those examples if for the other methods to even reach our method, which doesn't use any examples at all. To put this in perspective, 750 is about like half of the labeled data that occurs per task. So it's a very significant amount. Again, the metric here is omega, so higher is better. And so, we're actually competing, even though our method does not use any replay data, it's actually competing with methods that do use replay, which is really cool to see. And so that's the key takeaway. Ours does really well with no core set and competitive with methods that have to store data, core set methods. The other cool thing is essentially that when we do have correlations, global distillation, which is what this the prior state-of-the-art method that used web data for unlabeled data just fails catastrophically. So there's something in there, there are assumptions in there through its distillation that essentially there aren't correlations to the past tasks in the data. And which is interesting to see. So this correlations issue, which I think is actually something that you might get in real world streams, and I'll talk about how we want to actually move to that. Under that case, the past state-of-the-art work or fails, and while our method is actually still state-of-the-art, which is really cool to see compared to a bunch of methods that don't use core set as well. So that's kind of the key takeaway. So essentially, or sorry, I guess here, I think we do use some core set. So here, there's global distillation, which is the prior state of the art, and ours is much better. So, and it's cool to see again that different distributions of unlabeled data actually does matter to different methods. There's baked in assumptions to these algorithms about the distributions, which is not often made very explicit. And that's why we need to have rigorous methodology and experiments to actually simulate these types of things. And again, we use a small core set in this case. If you do no core set, I think a lot of things fail in the correlation case. So actually, this is a cool area of future work where if you have realistic streams of unlabeled data that are highly correlated with past tasks, how do we deal with that? So that's something that I'm definitely interested in doing future work for. We also show that we can scale to larger data sets like Tiny ImageNet, where you have more kind of classes, 200 classes and so on. And here under the no correlation setting, again, we do really, really well compared to all the other methods. Okay. So one thing that I didn't talk about is how we do out of distribution detection. Like I mentioned, this is using some state-of-the-art methods that we developed in CVPR 2020. And the key idea for out of distribution detection, which I'm going to go through a little bit because I think is really well kind of related to a lot of these continual learning problems, is essentially the out of distribution detection problem is learning a binary classifier that, again, given a model, you're training it on some training set, given new examples that either come from that training set or other data sets, can a binary classifier tell whether it's in or out of distribution. And again, we used it successfully in that continual learning setting. And by the way, one thing that's interesting that we've done in this CVPR paper is in the past, people have done out of distribution detection with things like non-semantic changes like corruptions on data and noise. But we actually also looked at semantic shifts, that is new classes. Obviously, if you have completely new categories from the training set, which is actually what the continual learning setting tests, the out of distribution detection problem is actually much harder. And that's where our method shines really well. That's why we were able to use it for that semi-supervised continual learning. And again, the key idea is just a binary classification problem. You come up with some scoring function that essentially tries to separate using a threshold, whether it's in or out of distribution. That is the problem. And there's lots of previous methods. You can obviously try to use the softmax probability, but that's very known to be very overconfident when you're using out of distribution or you're using only in distribution data to train it. There's lots of other methods like Odin that use temperature scaling and other things, and the Mahalanobis distance, which builds some density models. One of the key things is all of these methods, the later methods that compare to the simple baseline, actually use some out of distribution data to train it, to tune the hyperparameters, I should say. And so we are looking at the case where you don't have out of distribution examples to actually do anything. All you have is in distribution data, and you want to be able to train a model and a scoring function that comes from that model, either the features or the predictions, that can separate in or out of distribution data. And actually, so that's their motivation, is that first of all, the baseline that just uses softmax probabilities is obviously very overconfident. And so because it has a closed world assumption, right? Softmax induces a competition among the categories, and it's a closed world competition where you can't have other things in there. And so what we actually did in the CVPR paper is something interesting, which is looked at, what if you actually explicitly model some probability of the distribution being in and out during training. And again, this is trained in a soft manner and only trained within the in-distribution data. But of course, the in-distribution data is very varied. You might have outliers and things like that. And so what we did is, I won't go through the derivation, but we started from this idea of explicitly modeling like this latent variable of whether it's in or out of distribution, or to what extent is it in or out of distribution within the training set. And we did some law of conditional probability and basically divided this into a divisor dividend structure. And what's cool is once we did that math, we actually had a bias in the architecture where we had two branches coming from the architecture to model this divisor dividend structure. And these H and G functions actually can be any neural network. So it can be a simple learned parameter, or it can be actually a complex neural network by itself, which is really cool. And so that's the key idea. We have some math where we explicitly model this latent variable of whether something or how much something is in or out of distribution, even within just the training data. And then we add architectural bias to model this. And then we just train this model during training. And then we have a scoring function that essentially uses this, for example, cosine or other. You can come up with many different scoring functions to try to say, is it in or out of distribution using this model? And what we showed in that CVPR paper is that we get state-of-the-art out of distribution detection results. I'm going to put a plug for our recent NeurIP Spotlight, which actually comes up with a geometric interpretation for classifiers similar to prior works, where you have a feature norm and an angular component to a classifier. And actually, we come up with a better calibration and eventually out of distribution detection method. I'm not going to go into this detail, but we actually can do out of distribution detection much better now. The semi-supervised continual learning stuff was before this, so we didn't use this, but we've actually since used this for other semi-supervised learning methods like object detection, and it works extremely well. So please check it out. I don't really have time to go into it, but it's a cool geometric interpretation for out of distribution detection and calibration. Okay, so those are kind of the two kind of papers that I wanted to talk about, which again, get rid of replay from past data. One uses a generation process from the discriminative model. The other uses unlabeled data. And again, we try to do some scientific experimentation with respect to different distributions of unlabeled data. I think moving forward, there's a lot of exciting directions. The obvious question is that we use Cypher 100 to model these correlation structures. But what we want is, for example, there's some cool work in iClear, not our work, some related work that took few shot continual learning and actually generated data from a photosynthetic simulation environment as the agents move through it. And again, this really hammers home the idea we had, which is you have a mixture of labeled and unlabeled data as agents interact in the world. And we really want to leverage those sets of free data essentially to minimize catastrophic forgetting as much as possible. And so we want to deal with this under distribution shifts, new categories, or even different noise, or moving from home environments to office environments and so on. The other thing, is you can use this to stabilize representation learning. Obviously, self-supervised learning is something that has become really hot, and there's a lot of work now with continual learning, and I mean, pretty much every type of learning, and using self-supervised learning losses to try to stabilize representations, and also maybe multimodal settings where you either have vision and language or multiple modalities and things like that. And I really want to, again, just push this combination of, okay, now we have somewhat of a handle on continual learning. At least we understand the problem. We have a set of methods. How do we actually move this to more realistic embodied settings? Because I'm really interested in this connection between computer vision and perception and robotics. And so, there's lots of applications, both in terms of efficient fine tuning. If you have a robot moving through the environment, you want it to do continual learning in a few shot kind of setting, online, on a Jetson kind of board that has, very limited computation and memory budget as well. So how can we do such efficient continual learning, I think, is something that I'm really interested in. And of course, there's some cool biological perspectives as well. As we start dealing with more streaming data and things like that, I think there's a lot of cool things there. Okay, so I want to take some questions. So I'll summarize. Continual learning is obviously a challenging problem, and data replay, I think, is a very dominant method these days. You'll see a lot of papers that replay data. And so really we tackled kind of the exemplar-free method that doesn't actually do replay, either through generation from a discriminated model or just free unlabeled data you might have access to in the semi-supervised case. And there's a lot of cool future directions that I'm really interested in. And this combination between, distribution shift, self-supervised learning, and semi-supervised learning, I think there's some cool kind of unification that we can try to do across these different things. I want to thank all my funding, and of course, again, all the credit to all the cool work is to all my PhD students. They do everything. So I do want to acknowledge them. And again, if you want to look up the details, the references are below. So with that, I will take questions.
So I have a question, and thank you for the
Absolutely.
presentation. It was really interesting.
Sure. Cool.
So I'm very interested in efficient learning in terms of, like, as you continue to get more examples, keep updating your model, but you have a limited amount of time to do that. And it seems like one of the things that seems striking to me is that the model obviously has a lot of information about all the training data, it seems. So you can regenerate examples, or even if you had all those examples saved. The issue is that you have to spend a lot of time, like, going through those examples again and again as you continue to get new examples for any kinds of replay methods, whether it's through dreaming or just through your data. And so I was wondering, like, do you know of any, I'm not expecting you to know I'm not expecting like a complete answer to this, but do you know of any works or any directions where you can take advantage of the fact that the model already has this data built in, or where you're able to, like, get many of the benefits of a replay, but by taking advantage of, but based on, the model more directly, instead of needing to, like, spit out and then, cycle through again the examples.
Right. I mean, that's a great question. Honestly, I don't really know. I think obviously feature distillation and all these other methods try to leverage it as much as possible, what the prior model knows. Again, I think without generating data, or I mean, one thing I should say is unlabeled data is free, so you don't actually have to generate data. That's one reason I like unlabeled data that's available, because you don't have to spend the time for the generation process. But I honestly don't know of methods that can somehow use the implicit knowledge of the neural network without making it explicit, right? So yeah, I mean, obviously batch norm and kind of those statistical kind of things, but again, it's kind of a distillation type method, except rather than the distilling features or predictions, you're somehow adding information from the prior statistics, or some summary statistics from the prior data. Other than that, I mean, that's $1 million question. Yeah. I think there's, there's obviously the other approach, which is kind of growing neural networks. I think with vision transformers and things like adapters, which we're looking at in language, is very well utilized, where you have large transformers, but you have tiny learnable components in there that you're modifying for new things. I think is a really interesting avenue as well. In that case, you are adding parameters, right? So yeah, I other than that, I'm not familiar with better. I would love to see. Yeah, I think I've thought of some ideas in the past, but yeah, I don't think any of them have worked. So I think it's a really challenging problem. Yeah.
Thanks.
Yeah, I have I guess the question on the, so I'm very interested in the final, like the efficient, like online continual learning setting, doing a few shot like incremental learning on a JSON-like board. I'm just like curious, is there like any like related work or past work that has been done that's sort of like related to this direction, or is it like a, a totally fresh direction to explore?
Right. So like I mentioned, there is this wandering world from iClear, and I believe there's several follow-ons as well. So here you are again, and you can make it as streaming as you want. You're kind of gathering, progressively new amounts of data. One interesting thing is that the Wandering World does it in a instance-based classification manner. So you're classifying like chair instances rather than the class of chairs. And so that's actually makes it easier. And we've actually started working on class level versions of that. So we are working on that. I think there are some follow-on papers that cite this paper. So I would look at the citations for this paper that I think are in submission right now. So yeah, there are people definitely starting to look at it, but I would say it's pretty fresh. And again, it's I think a pretty unexplored topic. Yeah. Obviously, there was also on the other side streaming continual learning, looking at not like efficient necessarily, but looking at ways to just use like single examples. So you're just pushing the mini batch size down. You can't necessarily gather like 100 instances and do a mini batch update. You actually update the model parameters as you get each instance in a streaming way. So that's a whole class that is much better studied, I would say. But the kind of efficient continual fine tuning with respect to like computational or number of updates efficiency is certainly underexplored. I don't remember, there are some citations that cite the Wandering World. I don't remember the specific papers or where they came from, but
yeah, thanks for the answer. I will definitely like, check out the I guess the citation. And I don't know if it's I guess do you have the like answer off the top of your head, but like do you have like any I guess suggestions for like I guess good works in the like like the streaming continual learning that I can take a look at?
Yeah, so some of the citations, I'll probably fail at going back to that slide, but there are some citations in this when I talked about related work in the streaming case. Of course, that's only a few of them because I only picked a few for the slide, but feel free to email me and contact me and I can send you some. Yeah, there are definitely some cool works and not all of them are published in computer vision. By the way, there's some actually cool works published at ICRA and other kind of robotics, since there's a heavy tie into, obviously a robot doing continual learning.
Okay, yeah, thanks.
Yeah, definitely reach out and I'll send you some.
I'm afraid I have to thank you and leave precipitately, but I do want to thank you very much. That was most interesting.
Absolutely.
Thank you.
Okay, thank you. I really appreciate the opportunity.
I have one more question.
Sure.
So if I remember correctly, this wandering within a world is trained on a simulated data or synthetic data. And if you want to do continual learning in real data, then there are other kinds of challenges. Like first, there's a large shift in distribution going from synthetic to real data. So are there any work that are being used, like for example, using habitat or other data set which are more photorealistic to do this and see if the same method translates well on real data or not, or do you need different kinds of losses to do from synthetic to real?
So I think that's a great question. And by the way, I have some co-advised student with Drew Batra, who's from Meta, so he does the habitat stuff. So we're very interested in that, in generating that kind of data, which I think simulators are great for. There is, I believe in it comes from CMU, there are some data sets, I believe it's from Abhinav's group, that looks at ego-centric data, so streams of ego data. I will have to look up the reference, but I believe they're doing continual object detection from what I remember. And so they're looking at real world data and trying to continuously learn new object detectors from what I remember. And so there are, I should have mentioned that in the previous answer as well. So there are a few kind of new papers in submission or coming out now that do this. So yeah, again, if you send me an email, I will totally send you the reference. I can't think of it off the top of my head, but I believe it comes from CMU. But I do believe one nice thing about simulation is that you can generate a lot of data. You can get nice ground truth, right? Dense ground truth. You can actually think about multimodal and depth data and other things. So I think there's a lot of cool benefits to simulation as well. And these days, like you mentioned, habitat, for example, is super photorealistic at this point. So I don't think there's going to be, there's obviously always going to be some distribution shift, but obviously the distribution shift from this older works and habitat would be much less to the real world. Okay, sounds good.
Are there any other questions? Yeah.
Thank you.
Awesome. Thank you very much for the opportunity.
Thank you, Zol. Thanks for your time.
Yep.
Thanks for the great talk.
Yeah, it was a great talk. Thanks.
Thank you. So yeah, if you can send me the recording, that'd be great.
Yeah, sure. Thank
Do
you.
you mind if I put it online, or is that I don't know? I